Imagine a computer chip that doesn't rely on streams of electricity, but instead uses individual particles of light, photons, to process information. This isn't science fiction. It's the foundation of light-based quantum computing, a field that's rapidly moving from theory to reality. These quantum photonic chips guide photons through intricate microscopic channels, harnessing their unique quantum properties, like superposition and entanglement, to solve problems that are impossible for even today's most powerful supercomputers. By manipulating light at the quantum level, researchers are opening doors to entirely new ways of computing. This revolutionary technology could transform fields like drug discovery, materials science, and chemistry, allowing us to simulate complex molecules and materials with a level of accuracy never before possible. It could lead to breakthroughs in medicine, energy, and manufacturing. Quantum photonic chips also promise fundamentally secure communication. Because any attempt to eavesdrop on a quantum channel disturbs the photons, it instantly reveals the presence of an intruder, making hacking virtually impossible and ensuring privacy like never before. The journey begins in specialized laboratories, where scientists and engineers work tirelessly, pushing the boundaries of what's possible. Each breakthrough, no matter how small, brings us closer to integrating this transformative technology into our daily lives. The potential applications are vast, spanning artificial intelligence, climate modeling, secure global communications, and beyond. The impact could touch every aspect of society. We stand at the dawn of a new era, one powered by the purest form of energy, light. The possibilities are limitless, and the future is just beginning to shine. Turning a fragile lab prototype into a practical, scalable product is a journey filled with obstacles and innovation. Transforming a single, handcrafted quantum chip into millions rolling off an assembly line is a massive challenge that pushes the boundaries of science and engineering. First, scientists must create a standardized, robust design that can survive outside the controlled, perfect conditions of the laboratory, one that can handle the real world's unpredictability. Next comes developing a precise, repeatable manufacturing process. Every channel, every component must be identical, because even the tiniest flaw can ruin quantum performance and render a chip useless. Engineers rigorously test and refine each step, pushing yields from just a handful of working chips to the majority of every batch, constantly troubleshooting and improving along the way. Building a reliable supply chain for specialized materials and equipment is essential, creating a global ecosystem that supports this new technology from raw materials to finished product. The shift from scientific discovery to industrial production is a demanding transformation, requiring new skills, new partnerships, and a relentless focus on quality at every stage. Only by bridging this gap between the lab and the factory floor can quantum photonic chips become part of everyday technology, powering the next generation of devices. The journey from a single chip to a million is long and complex, but the rewards, revolutionizing technology and shaping the future, are truly immense. Modern chip foundries are engineering marvels, and the dream is to adapt them for quantum photonics. Instead of building new factories, we aim to use existing ones, lowering costs and accelerating innovation. But quantum chips require new materials, stricter tolerances, and ultra-pure processes. Tiny defects can destroy quantum information. Preventing quantum decoherence is critical. Even small vibrations or impurities can ruin a chip. Foundries must invent gentler manufacturing and new on-wafer quantum testing methods, since you can't just plug in a quantum chip. Solving these challenges is key to mass production. The foundry model could make quantum photonic chips accessible worldwide. The future of quantum technology depends on mastering this transition. After fabrication, quantum chips face the challenge of surviving outside the lab. Packaging must shield them from physical and environmental disturbances, creating a protective bubble for quantum operations. Aligning optical fibers to microscopic channels requires robotic precision. Just a micron off, and the chip fails. The package must also manage electrical connections and temperature, all without introducing noise that disrupts quantum states. It's a complex, multi-layered system, essentially a life support unit for the chip. Without perfect packaging, even the best chip is useless. Packaging bridges the quantum and classical worlds, enabling real-world applications. It's a critical, often overlooked step in making quantum technology practical. Quantum photonic chips must work alongside classical hardware to be truly useful in real-world applications. While quantum technology is powerful, it cannot operate in isolation. Its full potential is realized only when it is seamlessly integrated with the classical systems we already rely on every day. Integration is like adding a powerful new instrument to an orchestra. Quantum chips need CPUs, memory, and networking to function as a complete system. Each component plays a unique role, and together they create a symphony of advanced computing capabilities that neither could achieve alone. Translating between quantum and classical information requires sophisticated electronics and software. Specialized interfaces and control systems are needed to bridge the gap, ensuring that data can flow smoothly between quantum processors and traditional computers. This process involves not just hardware, but also advanced algorithms and error correction techniques, making the integration both a technical and creative challenge. This hybrid approach lets AI and quantum chips tackle problems neither could solve alone, like simulating molecules for drug discovery, optimizing complex systems, or analyzing massive datasets with unprecedented speed and accuracy. The future includes quantum networks, where chips communicate securely over optical fibers, enabling distributed quantum computing and opening the door to new forms of secure communication and collaboration. System-level integration is about orchestrating all components to work in harmony, from the smallest chip to the largest data center, ensuring reliability, scalability, and efficiency. Only by merging quantum and classical can we unlock the full potential of this technology, creating solutions that were once thought impossible. The quantum-classical partnership is the foundation of tomorrow's breakthroughs, driving innovation and shaping the future of science and technology. Every quantum chip needs a reliable source of single photons, the heart of the machine. Shrinking bulky lab setups onto a chip is a huge challenge. On-chip photon sources must be uniform and precise. Quantum dots, tiny defects in materials, can emit single photons, but making millions of identical dots is tough. Variations ruin quantum algorithms, so manufacturing must achieve atomic-level precision. Researchers are developing new materials, tuning methods, and alternative processes to ensure perfect photon sources. Cracking this code is essential for large-scale, fault-tolerant quantum computers. Mass-producing high-quality photon sources will unlock the next era of quantum technology. The future depends on mastering this fundamental step. As these challenges are overcome, quantum photonics will transform our world. Medicine will see earlier diagnoses and personalized treatments, while scientific discovery accelerates. Our digital lives will be secured by the laws of physics, not just code. AI will solve problems once thought impossible, revolutionizing industries from logistics to climate science. Quantum computing will democratize access to immense power. Startups, researchers, and creators will all benefit. The possibilities are limited only by imagination. The journey is just beginning, and the future is ours to shape. As chips of light move from science fiction to reality, we all have a role in building the illuminated world of tomorrow.